We're currently trying to prove the equivalent of the jump discontinuity, but in a three-dimensional context. And the way that works is as you approach the point that you're interested in, P, from different directions, different paths, your limit value will not exist because you'll have different limit values. And that will show you that the limit fails to exist at that point. So the one we already did here, we did the x and the y-axis, and it worked out very nicely because the limit values were not the same, and therefore there is no limit as I approach that point. So now I'm going to do a slightly more difficult one. 4xy over 3x squared plus y squared. Now, we start off with the domain briefly, because of course, if 0, 0 is within the domain, this really isn't a problem, and you can just substitute in your value. But of course, looking ahead, we won't be able to, because if you put 0 in for x, 0 in for y, we would have division by 0. So we notice that 3x squared plus y squared cannot be 0, which means that xy cannot be 0, 0. And that's the only time that graph would be equal to 0. All right, so then our domain is all xy in r squared except 0, 0. There's our domain. Which for the graph below means I want to put a little hole at the origin, which of course is larger than the origin itself, but it's a graphical representation. And the domain is every other number, the whole of the xy plane, all of r squared, except for that point. So now I want to find some paths. I want to approach that point from different directions. So I'm going to start off with what I did last time. I'll start off with my x-axis. So that'll be path number 1. We'll approach on the x-axis, which would mean that y is equal to 0. So that transforms our limit. Instead of xy approaching 0, 0, it will just be x approaching 0. And then it'll be 4x times 0 over 3x squared plus 0 squared, which is the limit as x approaches 0 of 0 over 3x squared. Okay, well, this is 0 over 0, which is technically indeterminate. However, it's 0 over some function squared, and so it's even though 0 over 0 is indeterminate, this is not indeterminate. This is going to be 0 because it's 0 all the way in up until that point. So it's 0 over, let me put it this way, it's 0 over something squared, or 3 times something squared. And so whatever that something is, it'll be a number. So it'll be 0, 0, 0, 0, 0 all the way up until you get to 0 itself. All right. Similarly, the y-axis is actually going to have similar problems. So if I put the y-axis, which is our path number 2, and in the last problem this worked out, and path number 2 was all we needed. But I think we're going to run into a little bit of problems here. Matter of fact, I know we are. If I let x be 0, I'm going to have the same problem in my numerator as I did before. It'll be 4 times 0 times y over 3 times 0 squared plus y squared, which again is the limit as y goes to 0 of 0 over y squared, which is 0. So far, I'm not proving what I want to prove. My goal here is to prove that those numbers don't exist, that the limit does not exist. And so far, I'm not proving that because I've got that they're the same. And I know, quote unquote, that this isn't going to work out because the problem told me that that's what I was trying to prove. So that means I need another path. Well, there's infinitely many paths radiating around this, right? Perhaps an easy one to try would be coming in on the diagonal, y equals x, right? So let's try path number 3. Y is equal to x, which is the diagonal 45-degree line, right? All right, well, let's see. This is the limit as xy goes to 0, 0 of 4x times x over 3x squared plus x squared. And it just occurred to me, I was what the pause was. I was thinking, well, if I substitute y for x. This is no longer a limit as xy goes to 0, 0. It's now a limit as x goes to 0 because I'm going to sub in x for y. You could do y. I just did x. So I let y turn into x. You could reverse it and make it 4y times y over 3y squared plus y squared, whichever way you want. So this would be the limit as x goes to 0 of 4x squared over 4x squared, because 3x squared and 1x squared is 4x squared, which is the limit as x goes to 0 of 1, which is 1. And we're done. Because now I prove that coming in on that diagonal path is heading to a different number than when I head in on the axes. Therefore, the limit does not exist. Which is what I was trying to prove. Right. All right. Well, let's do it again. Let's try some more. Actually, let me first show you on Maple really quickly what's happening here. Yeah, this is the right one. So 4xy over 3x squared plus y squared. As you can see, as I approach 0, 0, I'm getting 0. But if I do the overall limit, limit of 4xy over 3x squared plus y squared for 0 and 0, you can see that the computer says it's undefined. And here's what's happening. Let me make this a little bit larger if I can. So as we approach along an axis, right? So if I look down the barrel of the x-axis, right there, it's 0 all the way down. If I look at on the y-axis, over here, there's the y-axis, it's zeros, right down the center, 0, 0, 0, 0, 0, right down the middle. But if you come on the diagonal, you can see, oh no, right? It's coming to 1 all the way up, right? So it's a very interesting shape. It's like a folded piece of paper. And so it's going to different places as we approach 0, as we approach that origin. And of course, if I flip it all the way down so I can look down at the origin itself is not part of the domain, right? So that's that graph we have on our paper with the hole at the origin. But you can see if I come in from the top, I'm on that diagonal line, that ridge, it's at 1. If I would have done negative x, I would have actually been at negative 1. See how down here at the bottom of that fold of paper. So one diagonal is at 1, one diagonal is at negative 1. The axes themselves are at 0. They're going down the middle at 0, 0 all the way down. So it's a very interesting graph. Fascinating. All right, so now let's do another weird shape and see what's going on here. So I want to take the limit as xy goes to 0, 0 of this particular graph. You can imagine that 0, 0 is excluded from the domain again. I'll prove it. So the domain would be, again, 0, 0 would cause division by 0. So it's going to be all xy in r squared except the origin, because the origin would cause problems. So that means that my domain graph would be a hole around the origin. Everything else is fine. All right, so let's pick a path. Well, we liked the axes fine. We can try the axes. Worked out beautifully on the first example, right? So path number 1, working out great. So the x-axis would be y is equal to 0. Let's see, that's the limit as x goes to 0, 3 times x times 0 squared over x squared plus 0 to the 4th. And we're in the same boat we were. That's the limit as x goes to 0 of 0 over x squared, which is 0. And actually, I'm going to approach path number 2 also with blue, just because these are going to work out to be the same. So path number 2 is the y-axis. And we're going to be in similar trouble. If you let x be 0, it's going to cause the numerator to be equal to 0. So it'll be 3 times 0 times y squared over 0 squared plus y to the 4th. And that is, oops, sorry about that showing up on my screen. And that is equal to the limit as y goes to 0 of 0 over y to the 4th, which is again 0. All right, so that didn't prove anything. And I know this limit doesn't exist, so I've got to prove it. All right, well, let's try the diagonal line. So let's see if path number 3 helps at all. We'll come in from the diagonal like we did on the last one. Okay, so path number 3, y is equal to x. That'd be the limit as x goes to 0 of, I'm just going to substitute 3x times x squared over x squared plus x to the 4th, which is the limit as x goes to 0 of 3x to the 3rd over x squared times 1 plus x squared. I'm just kind of simplify as I go. So that'd be the limit as x goes to 0 of 3x over 1 plus x squared, which is 0. Right? When you substitute, you're going to get 0 over 1, and 0 over 1 is 0. Grr. So that was that diagonal. That didn't work. What about the other diagonal? What if I come in this way? What if I use y equals negative x? So the limit as x goes to 0, 3x times negative x squared over negative x, oh, sorry, it was x squared. X squared plus negative x to the 4th is, lo and behold, the same thing as above. It's x goes to 0, because when you take a negative and you square it, it turns it positive. So it's 3x to the 3rd over x squared times 1 plus x squared. And so it's 0. Boo. All right, so all the regular lines are not working well for us. We could try another line like y equals 2x. I'm going to try something different. Let's go with something other than lines. Maybe something can be fun like a parabola. So let's come in on a parabola like y equals x, or excuse me, x equals y squared. What if we try that? Kind of a sideways parabola. There's lots of ways you could do this. I just figured let's try something different. So I'm going to take the limit as x goes to 0. Actually, this will be easier if I do a substitute. Let me do y equals to 0. And then I'm going to put where x was, I'm going to put y squared. So it's 3 times y squared over y squared squared plus y to the 4th. That'd be the limit as y goes to 0, 3y to the 4th over 2y to the 4th, because that's y to the 4th and that's y to the 4th, which is the limit as y goes to 0. Oh, look at that. There it is. Now, is that the only way you could have done this? No. Try lots of different things. You could try x equals negative y squared. You could try y equals x squared. You could try, lots of different paths. Maybe a diagonal line would have worked. Maybe y equals 1/2 x would have worked. Who knows? Just try different paths. I generally try the axes and the diagonals first, and if those don't work, go with something different, like a parabola, and just see what happens if I'm trying to get through the origin. So 3/2 is not equal to 0, therefore there's no limit. So 3/2 does not equal 0. Therefore, or that implies, the limit as xy goes to 0, 0 of this function does not exist. It took us a while to find the right path, but we got there. And as for how to find the right path, trial and error. I always start with the axes, then I do the diagonals, and then if those don't work, all bets are off. Try a different diagonal line, try a parabola, try a cubic, see what happens. If you want to see this graph, in case you're interested, you can see that Maple's telling you that it's not going to work. It's undefined. This is the graph. It's kind of fascinating looking, right? So if you look at it from up above, you can see, oh, let me make this a little bit larger. You can see the hole right through it at the origin, right? So it's a little pinhole right there that you can't have. But as you approach from different venues, so if I look down the y-axis, it's 0. If I look down the x-axis, there it is, it's 0. If I look down the diagonal, right, y equals x, right? It's not doing anything good, right? But then if I take that parabola shape, it's going different places. So it's a fascinating little fold of paper to look at.